What's the most useful household appliance that you have?
That's definitely the washing machine.
When did you buy it?
I bought it 2 years ago. Actually, my mom gave it to me as a birthday present.
Is it expensive?
I don't think it costs that much.
Hi, and welcome back to Understanding Motors. Last episode, we established how you can reliably control your brushed motor. So now we're basically good to run this thing forever, right? Well, not exactly, because, like all things, motors can and do break. If an electrical system is beyond the testing and development stage, the primary method of long-term degradation of a brushed motor is brush wear. As I mentioned in episode 2, though I chose to depict brushed commutation as point conductors on the nodes connecting with larger conductors for the brushes, as I believe it's easier to understand, real brushed motors use larger conductive strips connected to each of the nodes, which, as the motor turns, contact smaller conductor brushes, as shown here. The brushes and conductive strips on the rotor will, over time, become worn out or deformed. They will then no longer be able to reliably conduct electricity, and then all the work we did last episode is out the window. Additionally, as motors wear, brush bounce becomes more of an issue. Brush bounce is the making and breaking of contact between the brush and the motor phase due to vibrations at higher speeds. In brushed motors, brush bounce is always an issue that limits the speed at which you can spin your motor. However, over time, this can become worse. In addition to wear on the brushes, bearings and other such moving parts can wear over time. Though barring abnormal circumstances, they would not become faulty before the brushes. The more acute method of failure for brushed motors, and actually all motors, is overheating. The wire coils in the motor are typically made of magnet wire, which is basically just regular wire with an unusually thin coating of non-conductive insulation, which allows it to be more tightly coiled together in the motor. Like all non-superconductor materials, these wires have some non-zero resistance, which is proportional to their length and inversely proportional to the cross-sectional area. As current passes through the coils, they will experience Joule heating, which is resistive energy loss that goes to heating the wires. This energy loss is proportional to the resistance of the wires and a function of the current running through the system squared. The first law of thermodynamics says that because there's no work done by the resistance of the coils, the change in internal energy is only a function of heat transfer. Therefore, if the energy going to Joule heating is greater than the heat transferred out of these coils, the temperature of the wires will increase. To make matters worse, as temperature increases, the resistance of the windings will increase. This causes our Joule heating to go up, again increasing our temperature. We need to keep an eye on what the limits of heat transfer are, because if our wires get above a certain temperature, typically around 150 degrees Celsius, the insulation on the wires will melt and the coils will short together, ruining your motor. I want to take a pause here for a second and bring this idea back to practically running a motor. The issue of overheating is the basis for the continuous current rating you'll see on your motor's datasheet. What the current rating essentially says is that, assuming normal temperatures and conditions and that there's no extra heat sinking done on the motor, you could run this specified current through your motor continuously without overheating the motor and melting the winding insulation. When operating a motor, you can push current through it which is notably higher than this rating without damaging the motor, just not for extended periods of time. This rating essentially gives you a range where, assuming normal operating conditions, you will definitely not burn your motor out. Beyond those ranges, it's up to you to do the thermal analysis to make sure your motor won't overheat. To better understand the heat transfer out of the wires, we're going to do a quick thermodynamic analysis of the system. Much like an electrical system, where current is driven by some voltage differential and the magnitude of that current is dictated by the electrical resistance of the system, heat transfer into or out of a body is driven by a temperature differential and its magnitude is dictated by what is essentially a thermal resistance. In the motor system, we can separate the thermal resistance into 4 steps: the resistance of conducting the heat from the wires to the outside of the rotor, the resistance of convective heat transfer from the rotor across the air gap to the stator, the conductive transfer from the inside of the stator to its outside, and then the convective transfer from the stator to ambient air. It's worth noting that if you have additional heat sinking to some external ground or plate, the last thermal resistance will be significantly decreased, as it will also include conductive heat transfer. Additionally, each of these steps will transfer heat via radiation. However, this is negligible when compared to the transfer via convection and conduction. The heat transfer out of our system is equal to the temperature differential divided by the net resistance. So, if we want to be able to push more current without overheating our motor, we need to decrease that thermal resistance as much as possible. As you may or may not know, it is reasonable to expect that an unforced convective heat transfer in air could be an order of magnitude less efficient than conduction through metals. With this in mind, the thermal resistance of the system is likely dominated by the two convective portions of heat transfer. If we can decrease these, we can help keep the motor at a safe temperature. As we already mentioned, heat sinking the outside of the motor to a thermally conductive plate or housing can definitely cut down on the stator to ambient resistance. However, there's very little we can do to improve the transfer between the rotor and the stator. The limits of heat transfer, as well as the issues of brush wear and brush bounce, are what led to the invention of brushless motors, as well as their recent adoption into basically every actuated appliance. Unlike a brushed motor, which has the windings on the rotor and a magnet on the stator, a brushless motor has the windings on the stator and its permanent magnets on the rotor. This cuts the thermal resistance from 4 terms down to 2, and completely eliminates the convective heat transfer between the rotor and the stator, drastically improving the amount of heat transfer for a given temperature differential. This means that, for a fixed amount of current running through the coils, the wires will be cooler in a brushless motor. Again, since resistance is temperature dependent, this results in an increased efficiency and the ability to push more current through the motor. This means that a brushless motor can be used to produce more torque than a brushed motor of the same size and weight. Unlike the brush motor, which handles commutation via physical contacts dictated by rotation, brushless motors rely on computer-controlled electronics to perform commutation. This means we don't have to worry about the quality of our commutation degrading over time. Additionally, since we no longer have to worry about the bouncing of brushes causing us to lose contact, brushless motors can be rotated significantly faster. So, by utilizing a more thermally efficient design, a brushless motor is able to produce more torque and mechanical power than a brushed motor of the same size and weight. However, with this new technology comes new challenges, and that is what we're going to start talking about next episode.